How about taking a look at some cyclic systems? To start with, we'll consider cyclopropane. This molecule has a plane of symmetry. The substituents have a cis relationship, and the molecule is achiral meso. The other two molecules in this 1,2 disubstituted relationship are enantiomers, with a trans relationship between the substituents. They are chiral and optically active. Next, growing the ring size, we'll view cyclobutane. Now, the 1,2 disubstituted pattern is similar to the cyclopropane case we just looked at, so we won't dwell upon it. However, the 1,3 disubstituted arrangement displays some interesting properties. Here is an example: on the left, cis, on the right, trans. Both are achiral, optically inactive. Hold on now. The cis looks like meso. We'll come back to that in a minute. So maybe you can say that it's achiral, optically inactive. But the trans, that's surely chiral, optically active. What's going on? We have drawn the molecule with a view from one direction. But that doesn't mean we mustn't consider other directions. What do we see if we view the molecules from the top, as seen here? Well, when seen from this angle, we can spot a plane of symmetry for either cis or trans relationships. Okay, I was being a little bit coy about calling the cis molecule meso, and that's because it isn't. For cis to be meso, there needs to be two other configurational isomers that are optically active. As the trans isomer is optically inactive here, thus the cis isomer is not meso. It's notable that there's no stereogenic centers here. Well, we've chosen an example with the same substituents, that's to say methyl groups. Okay, well, let's exchange one of the methyl groups for a chloro group. There. Now look for that top plane of symmetry. Yep, still there, so no change. Still, both isomers are achiral, optically inactive. Going from 4 carbons to 5 carbons, we will analyze cyclopentane. In this first example, the 1,2 disubstituted pattern, we can hopefully spot a plane of symmetry. What we have here is a meso molecule with substituents in a cis relationship to each other, and thus the compound is achiral. That isn't the only possible arrangement. These molecules share different orientations of the hydroxyl groups that are trans to each other, and the two isomers are enantiomers of each other. They're therefore chiral and optically active. Now we move on to 1,3 disubstitution patterns. Here, this molecule has a plane of symmetry. The bromo groups are cis to each other, and so the compound is meso. The alternative arrangement between the bromo groups here is trans. The two possible forms are enantiomers of each other. Here's another example of a tetrahydrofuran core with a plane of symmetry and a cis relationship between the hydroxyl groups. Thus, it's meso. What happens if we have two different types of substituents? So we will replace a bromo group with a methyl group. These two isomers have a cis relationship between the bromo and methyl groups. There is no plane of symmetry, and they are enantiomers of each other. These two stereoisomers are diastereomers of the prior cis arrangements. They have trans relationships between the bromo and methyl groups, and are enantiomers of each other. How about cyclohexanes? To start with, the 1,2 disubstitution with dibromo groups has 3 possibilities. Here we have the dibromo groups in a cis relationship to each other, and there is a plane of symmetry, making this meso. The trans stereoisomer has 2 forms that are mirror images of each other They are enantiomers. With 1,3-di substitution, the cis arrangement has a plane of symmetry again, making it meso. The diastereomers of this share a mirror image, and thus they're enantiomers. The bromo groups are in a trans relationship with each other. The case of 1,4-di substitution, either where the substituents are the same or different, both have a plane of symmetry. Neither has any stereogenic centers. This is true for either the cis or the trans stereoisomers. They are achiral and optically inactive. The cis isomer isn't meso, such as this molecule.